Good afternoon and welcome to the second lecture in our series of 3 lectures this week on aspects of quantum information science and engineering. These lecture series, the 3 lectures this week, are part of a community effort that recognizes World Quantum Day, and we had this ambitious goal to come up to basically organize about 1,000 events, learning events on quantum aspects, different aspects of quantum science and technology, between April 14, which was World Quantum Day, and the end of May. So we make a modest contribution at UTC in terms of the 3 lectures this week. There's also a website which summarizes all the activities that are underway under this motto in the community of Gig City Goes Quantum. And we have started a quantum initiative at the university, which also has a website which is a little bit longer, but if you Google on UTC and quantum, you'll be led to that website. It summarizes our quantum initiative. So today it's a real pleasure to introduce Dr. James Troop, who is the chief quantum scientist at Kairos Systems, which is a company, a small company, startup company located in Denver, Colorado. It's a space and technology company, and you'll learn more about it if you go to their website. But you'll learn a lot more today about sort of the technologies that they're interested in when in this lecture by Dr. Troop. Dr. Troop has a bachelor's degree in physics from the University of New Orleans. He has a master's in physics from Tulane University in New Orleans, and went on to get a PhD in computational science from Chapman University in Orange, California. Today he's going to talk to us about quantum networking, and within that I'll leave it up to him to see what kind of details he'll excite us with this morning. James?
Well, thank you very much, Reinhold. And first of all, let me say thank you to everyone for showing up and for inviting me here for this event and for these events for the first World Quantum Day. Hopefully there'll be many more. It's really important to get the message out about quantum technology. I'm sorry, my slides are advancing. I hit the wrong button. I'm not very good with technology, ironically. I'm a theorist, so it's okay. Let me go back to the beginning so I don't show all of my exciting slides ahead of time. So anyway, just thank you. This is a really important event to get the message out to everyone about these new technologies that are starting to develop, and hopefully you'll get a taste for what this is, why there's a big buzz about it, what the potential futures are, and maybe have some good questions that you can take home and think about in terms of what it's going to mean for your lives, hopefully. So, subtitle, what is this quantum internet? Why do you care? You might not care at the end, and that's okay, but I'll give you some reasons why I think you might want to care. And hopefully you get at least a 1-sentence definition that will make sense at the very end as to what it is. So this is the advertisement part of the show. This is Xeros, the company that was mentioned that I'm the chief scientist for. Give you the 30-second elevator pitch. We're a startup. The focus is distributing timing information down to the picosecond level, and our target is globally and securely. So you might want to, if you think about the global positioning system, it's essentially a timing system. It's a global timing network that we use for positioning, but that's what it is. It's a bunch of clocks that are synchronized and in orbit, and we have access to those signals. Those signals sort of run a lot of the infrastructure in the world, particularly telecommunications and cloud computing, and the accuracy of that system and all the other systems that came after it are sort of on the order of 10 nanoseconds, and sort of the accuracy of that. So this is basically a clock network with an accuracy of 10 nanoseconds. It's always there. It's sort of free when it works. There's some problems there in terms of jamming and spoofing, but it's a very, very good system. The idea here is to build a better system for the future. Because it's actually quite difficult to build that kind of system significantly better than say a nanosecond. And we're focusing on that using quantum technology, and in particular, a particular kind of entanglement that I won't specifically talk about, but it does use light. We're focused on space because we need coverage with satellites, but we're also looking at some fiber as well because we want it to cover as many users as possible. So that's the pitch. Now, I won't talk about that again. I can answer questions later if anyone's interested. Okay, so this has very little to do with quantum, but I wanted to give you some context for what a quantum network is by talking about classical networks. What do we mean by that? We sort of take it for granted these days, and so that's why I wanted to give some context. All these things were invented, and we're sort of inventing a new kind of network, so it's kind of nice to go back and look at what happened in the one we have. So if you start in 1837, a bunch of people were racing actually to figure out how to use electricity, electromagnetism to send signals through wires. The guys who first cracked it and got a good patent on it were in Britain. Their system was kind of complicated. It was sort of improved later by some Americans, and came what electric telegraph that you sort of think about in sort of the old movies. By the way, just as an aside, it was better because the improvement was digital. That's essentially the difference between the first one and the second one. They came up with the idea of using dashes and dots to do the encoding. So that's the first instance of using communication long distance with bits, basically. So then you go on, you invent the telephone. Bell Telephones founded a few decades later. Shannon, basically in his master's thesis, writes down an efficient way of doing classical digital circuits. It's a pretty good master's thesis. Then he invented information theory 5 or 6 years later during the war. After the war, they declassified it. It was published in 1948. So that's the beginning of classical information theory. So these things are all sort of coming together, and then in the early 50s, after the Soviet Union detonated the first atomic bomb in 1949, the US got very worried. We had only a few nuclear weapons. Supposedly the Soviets didn't know that. They probably did, but we didn't know that they knew that. And so we were worried about, being attacked if they had 5 and we had 5, maybe they're going to attack us first. So we put up radars over the poles to look for early warning for bombers, but they weren't coordinated. So they had to figure out a way to collect all that information and coordinate it, figure out where to send interceptors as fast as possible if that should become a thing. They invented a network to do that. Some people at MIT using computers that were being developed, networked those computers into their sensors, and that was sort of the first real world use case for a large distributed computer network. A lot of money went into that. Those people started a little ecosystem up in the Boston area around MIT in thinking about this. In the early 60s, right around the time they finished that, this person, J.C.R. Licklider, Lick as he was known, he was working for a company there, and he's a psychologist actually, but he was thinking about computers and networks, and well, if you put these together, it's a communication system. This is a human system. It's designed to help humans. So he came up with the idea of machine-human symbiosis and using computers and communication to help people do whatever they wanted to do. And he wrote some very thought-provoking papers in the early 60s. Well, he got hired at ARPA at the time, to work for the Air Force and the military to come up with ideas for networking computers better. So he basically started ARPANET, which became eventually the internet. So if you look at the history of that, this picture at the top left is ARPANET in December 1969. They started the program in November. That was set up and running before Christmas in 1969. There's four computers. One in Utah, one up in the Bay, and a couple in Southern California. So the thing on the bottom there is a picture on Wikipedia. It's a snapshot. There's a giant picture if you blow it up. It's a snapshot of the internet in early 1995. It's a huge fractal. It's very complicated. This is a tiny, tiny piece of what the internet is now. The internet is basically unmeasurable now. It started, though, on January 1st, 1983, which is kind of nice. This is when all the other little copycat networks started connecting to the ARPANET, and then they decided to have a common language called TCP/IP, and in that date, everyone started using that for communication protocols. That's the birth date of the internet. That's a long time ago, but it's not that long if you think about it from the first electric telegraph. A lot was invented there. So you think about all those technologies being invented at the same time leading up to that event in 1983. And then it just took off. The early 90s, commercialization took over. Netscape Navigator, 94. Anybody remembers that? It's a defunct company, but it was the first commercial browser for the web. And then I put a couple things that are a little bit interesting here. And I have 2012. I think this was started earlier, around 2010, but the EPB network here in Chattanooga with the 1 gigabit internet was completed in the whole area around that time, which, by the way, was the fastest internet on Earth except for Hong Kong at the time, I think. They had about the same speed. At least it was the fastest in North America. There may have been one in Europe somewhere. So that was a big deal. So I just wanted to put it in there because it's actually an important thing technologically, because this is very forward thinking for the city here to do this. And so it's also appropriate that just a few months ago, the first commercial focused quantum network was set up here as well in town. Again, small, a few nodes. Like there's 3 or 4 here in this network. Well, there was only 3 or 4 in that network too. So you don't know what's going to happen. So that's the important thing to keep in mind. It takes a lot of people to build these technologies, and that's why I'm here, is everyone should know this is coming. Think about how you can participate if you're interested, because there's going to be a lot of opportunity to do that. So that's a long slide, but I wanted to put that in there because I think it's important in terms of thinking about what I'm going to say about the actual physics and engineering. So now we jump into the physics, or the math, depending on your religion. Which that's a joke's funnier than it sounds, but I won't get into that later until the question period. So classical versus quantum. You can think of this in terms of classical physics and information. They're in some sense interchangeable for the purposes of this talk, hopefully not confusingly so. Classical information we think of as sort of simple, but if you just saw that last slide, everything there was built on that idea. A bit. It's a 0 or it's a 1. I have a physical system. I can encode that in it. I can read it out. I can hold it. I can send it. I can process it. It's a simple idea, but it has huge implications for society. What I'm going to say here is sort of the same thing in quantum mechanics land. It'll sound a little bit simple, but a little more complicated, but not that much more complicated. I replace the 0 and 1, which I've represented by the poles of that sphere there. That's the classical information world, 0 or 1. The surface of that sphere represents all the possible states that a qubit, a quantum bit, can be in. Okay, well, that seems like a lot more information, but there's sort of a trick with quantum information, with quantum mechanics and quantum qubits, which you need to really keep in mind, which is though it is a lot of information, you can only ever get out 1 bit. So you can code a bit in it, you can only get it out 1 bit. So what happens is that when you want to encode a classical bit into that qubit, you have to decide how you want to encode it. Now, if you have a bit, it's a 0 or a 1. The choice is made for you. That's, you have a system and it's clearly defined to be one state or the other. It's definitely one state, it's definitely the other. Well, in this case, you have a choice in terms of how you want to encode it. The qubit is the whole surface, but the representation of the qubit is defined in terms of this, what's called a basis. So if you see these lines, there's the red one, purple one, and the blue one. Those are 3 different bases that you could define your qubit with respect to. What it really means is that when I encode or read out information, those are the definite states. So if I'm using the vertical basis, which are defined by those 2 endpoints, I can choose the state to be one or the other of the poles. And then when I read it out, if I choose to measure it in that basis that's along that line, I'll get out what I put in 100% of the time, just like classical information. But what happens if I measure in a basis, say the red, the purple, the bluish basis, the plus minus basis instead? So if I encode a 0 into the vertical basis and I measure the other one, what happens? Well, I get out a plus or a minus. Now let's think, in terms of what does a plus or minus quantum state mean, it means I'm going to think of it as plus being a 0 and minus being a 1, just because you get two outputs. So every time you choose a basis, you get one or two outputs. We label one as 0 and one of 1 in terms of the output bits. So if I get a plus, I call it a 0. If I get a minus, I call it a 1. Well, if I've encoded 0 or 1 in that vertical basis and I measure along that plus minus basis, I will get a random bit, a 0 or a 1. So it's just completely random. So that doesn't sound very interesting, but hopefully later you'll see that it kind of is. You could also measure it in any other point. You can define any, draw a line through the center of that in any direction, and that would define a basis. Okay, also that's an important point. These are sort of preferred bases in the sense that they're the most different from each other, right? So if I prepare one, it's the definite state, say in the vertical basis, 0 or 1, and I measure in either of those two bases that are shown, I will get a completely random result. If I measure some other result, it'll be biased one way or the other, but essentially because those two output states are not equally distant from the two states. So I'm going to pause here for a second because I want this to sort of be a little bit clear. Now, people call this idea superposition. The idea is that if I say I have a 0 and I choose the 0 state at the top of the sphere, and I think about it in terms of the plus minus state, it's equal superposition of plus and minus quantum states. So it's a definite output if I measure in the 0, 1 basis, but it's completely uncertain if I measure in the plus minus basis because it's an equal superposition. The physical system's in a definite state. It's in the superposition. Because remember, we prepared it in a definite state. But from the point of view of a measurement along that line, you don't know what particular outcome you'll get in terms of that bit that you're pulling out of the measurement. But before you measure it, it was in that superposition state. Another key point is that after you measure it, and you get out one or the other, the 0 or the 1, and you get indicating a plus or a minus, it's definitely in that state. So it went from being in, say, the 0 state to the plus state because of the act of measurement. Because you interacted with the system and extracted that bit, it forces it to be one or the other of those two states that it's in before you measured it. So what's quantum about this, what's different from classical mechanics, is that the uncertainty in which of those outcomes we would have isn't because I don't know enough about how it was prepared. I can know perfectly that it definitely was in the 0 state, but I can't tell you what the output will be because it's just not in that other basis, because it doesn't, in some sense, quantum mechanics just doesn't allow you to ask that question. The idea that it's in a definite plus or minus state, well, it isn't. It's in a plus and a minus state. This is where you get statements like two states at the same time. Well, it's a very particular meaning of two states at the same time. It's a particular combination of those states. It's definitely in a definite physical state. There's no uncertainty about the state, but there is uncertainty about the outcome of a measurement in that basis of that state. And that's a little bit of a subtle difference, but it's a very important difference. And I also want to emphasize that the act of measurement of a state is a physical act. You have to interact with it. It changes the state. And a lot of the confusion that even the people that invented quantum mechanics had was, is that disturbance of measurement sort of because we don't know how we're measuring it, or if there's something uncertain about the state itself? Is there some underlying reality that we're just shielded from that's causing, explains those outcomes in some deeper sense? Or is it, this is just how it is? Spoiler, it's just how it is, but it's actually a pretty interesting question that I'm going to explore a little bit later. This essentially just repeats what I said. I have a bad habit of ignoring my own slides, so I'm just want to re-emphasize that measurement changes the state. So again, if I start in 0 and I measure along this axis, I'll get one of these two. If I get that state, it's definitely in that state. So if I measure it again in that axis, I'll get it again. It'll still be there. When I say that, I'm ignoring noise, right? Classical noise in the sense that of some uncertainty about my measuring procedure. So in the ideal sense, that's what I mean. Okay, so let's talk specifics. Particularly for networks, we need to encode this information in a physical system, not just a slide or math. We need physics, right? So a qubit, a really good qubit is a photon. So this slide is showing you what a photon is, sort of, but it's really classical it's just a classical field. Think of this as the electromagnetic field that represents the light propagating in the z direction into the slide. Well, what I'm about to say is all classical, then I'll get to the quantum. Well, the electric field is vibrating at some frequency based on the energy of the light or the color of the light along a certain direction. So there's different orientations of the field. This would be horizontal, vertical. You could also think in terms of what's called a diagonal polarization, which would be 45 degrees. So you just rotate everything 45 degrees. Those are two different bases representing the wave. So these are vectors. You can represent them again in any coordinate system you want. So that's just another way of writing the same thing. That's the classical version of the Bloch sphere I was talking about just a second ago. The difference being, though, that for quantum state, for quantum systems, or if electromagnetic field is quantized, I don't have a nice continuous amount of energy there. Anytime you interact with it, you only get out a discrete amount of energy. So the lowest amount, which is what we're going to focus on, are single photons. So when you measure this and you want to decide which polarization it's in, once you decide you want to measure along that basis, it's either going to be on one or the other, right? You're going to see a click in your thing saying the photon was in that polarization or it was in that. You won't see anything in between. You won't see some portion of it in one or portion of it in the other the way you will with classical waves. So it'll be one or the other. Again, that's the idea that there is an outcome. There's a discrete classical information that comes out of that measurement. In this case, a measurement of a qubit. So I wanted to emphasize that's how we're going to think about these physically, these qubits. The other thing to say is that this is really good. These things are really fast. They also don't interact with each other really at all, or very much with their environment. That's why we use them for communication via the free space, through fibers, and they're very nice for classical communication. They're also good for quantum communications. Okay, so again, I'm going to take that and dive in just a little bit deeper so that when we get to the more interesting things, it'll be hopefully clear. This is just restating what I said generally about qubits, but in the case of using photons as a qubit. A particular degree of freedom of the field is the one that I mentioned, which is the polarization, is sort of the most easiest to understand. There are others, but this is the one I'm going to use, and that a lot of people use for quantum communication is the polarization. So terminology, horizontal vertical basis, I sort of in the previous slide talked about what that is. If you think about it in terms of our sphere here, which by the way is called a Bloch sphere, so if I call it a Bloch sphere, that's what I mean. It's also called a Poincaré sphere, but that's a different, it depends on the context. So notation-wise, this is sort of the general Bloch sphere. And when I'm going to now think about this, when I think about it as a polarization, I'm going to think these bases are defining the orientation that I'm measuring the polarization in, or preparing it in, depending on the context. So let's think of 0 and 1 as horizontal vertical. So I'll be reading out or encoding a 0 as horizontal and a 1 as vertical when I'm measuring that basis. If I'm measuring in the diagonal basis, which is that one that's rotated by 45 degrees, then it'll be this plus minus basis. So plus will be 0, minus will be 1. There's this other basis that's sort of in there that goes in the other direction that defines the complex part of this. So everything on that circle defined by the first two bases are all real valued states. So it's sort of like real quantum mechanics without the imaginary numbers. We don't need those for the purpose of this talk, but they're there just to complete the sphere. So also, I'm emphasizing here that that's spatially rotated, because the physics are, if you remember that previous slide, that's the basis defined by rotating this 45 degrees and looking along those sort of in between directions. So that's spatially rotating, thinking in terms of measuring spatially. But if you think about it in terms of the Bloch sphere, it's actually a pi, because they're on opposite ends. It's just the way it's represented. So mathematically, if you thought about rotating these bases, you're actually rotating 0 from, if you start out in horizontal vertical, you're actually rotating the Bloch sphere by 90 degrees, not pi over 4. So that's just a difference between the way we're representing the quantum information versus the actual electromagnetic field. Don't worry about that. Just in case somebody was sharp and noticed that it looks inconsistent, it's because they're slightly different and there's a mapping between the two. Okay, so this is an exercise now in seeing if we understand what I just said. So we're going to spend a few slides on quantum key distribution as a warm-up, actually, to the actual main show in a bit. So who here has heard of quantum key distribution? Okay. I'm glad the Cubitech people said yes. I guess that's good. And the EPB people. So quantum key distribution, basically the idea, what is it? It's using quantum information, in this case photons, to create a secure shared random string between two parties that are separated. The idea here is that then you can use that secure key as input to some encryption program, typically as symmetric encryption. Don't worry about what that means, but it's just a way of encrypting information. It's very secure. The downside with symmetric encryption is it's very secure, but you need a lot of key, and you have to use it and sort of develop it. It's almost as hard to make the key as it is to just hand the message to the person. So you're trying to get around that problem. So there are ways to do this. Typically, they have very secure suitcases full of key, and then they put with a guy with a gun goes out and spreads it, copies around. Well, that's great, except if one of the copies gets lost, and then you need keys for everybody because you can't trust any of them. So this develops a key between two people immediately when they're, instantaneously, so, and continuously. So that's the purpose. So why is this, how does this relate to what I just said? Well, we're going to use polarization to encode a 0 or 1 at Alice. She wants to share this key with Bob, who's on the other end of a line, of either a free space channel or a fiber. So this is basically the gist of how it works. Each of them will have some entropy source. They'll have randomness source. Could be a quantum source, could be not, but it's some trusted entropy source where its random numbers are given to them. They use that as input. Alice will take one random bit and decide on a basis to encode, so either plus or minus or horizontal or vertical, so one of the two based on whether it's a 0 or 1. Then she'll take another random bit, and that'll be the classical information she's going to encode into qubit. She does that. She sends it through the channel to Bob. Bob has his own entropy source, a different one, and he takes a random bit, and based on what it is, he measures in the plus or minus or the horizontal basis based on the bit value, his bit value. He reads it out, he gets a bit of information. He records it, and they do this a bunch of times, which is what that slide says. By the way, just as an aside, this is a little table at the top to show you an example of this. And the bottom picture is actually a picture from, I believe it's a picture of the prototype that was built by some theorists at IBM in, I think, the late 80s of a quantum key distribution system. It was about a foot long and on a table like that. So they implemented it just to show that it would work. Okay, so they've done that a bunch of times. After it's done, Alice will then announce her basis choice for all those photons that she sent. She'll say, well, these are the bases I prepared them in. Bob will then look at that list, and for the ones that he measured, he will note which ones were in the same bases. He'll tell Alice that. And then she's going to actually announce, she'll pick some random subset of those and announce the bit value she encoded and tell Bob. And the reason she does that is that then they can sort of estimate the error rate of the information that was encoded, right? Because if those are sort of evenly distributed and you do it enough times, say you take half of them and check it, it gives you a good statistical bound on the error rate for the other things that weren't disclosed. And the reason that's important is because if you remember, measurement disturbs the state. An outside person, an eavesdropper who wants to read those bits, right? If this were classical, they can just read the bit. It doesn't change it. They can copy it. It doesn't, they can extract that information. It has no effect on the state. But since they don't know the basis, they can guess the basis, but they're going to be wrong half the time. So that puts a limit on, there's a limit to how little disturbance an eavesdropper can introduce into the channel. Theorists figured that out, so as long as that error rate is below that amount, there's a way to distill a secret key, right? So basically that limits any leakage of the key by knowing the bound on the amount of information that could have been leaked by someone measuring it. And that's how QKD works. There's all kinds of variations on the theme and ways of doing it, but at the end of the day, it basically comes down to conjugate bases, which is what those are called, that are one, if you measure one, you completely destroy the other, and measurement disturbs the state when you don't know the basis. That's how QKD works. Just to emphasize, this is sort of like a first generation network application because it doesn't require memory or any sort of processing at the nodes. You're basically preparing them and sending them and measuring them pretty much continuously, and it's sort of easier. I'd say it's easier. This was invented in the mid-'80s, early '80s, and these things became commercially viable in the last 5 or 6 years, really. So these are now out there, and you can buy them commercially. But it took a while to get to the point where they were potentially useful. There's also something you might hear out in the literature and you hear a lot about quantum these days. People talk about post-quantum cryptography. They're not talking about QKD. They're talking about a different way of doing cryptography using an updated version of sort of the public key encryption that we use now, but using a different math problem. The math problem that people use now for almost all encryption, all public key encryption anyway, is very susceptible to a quantum computer if it's big enough. So people are preparing for that, and they've got QKD to lean on. They've also got post-quantum crypto algorithms, which is all classical communication and classical encryption, but using a hard math problem. The difference being the same difference there has always been between symmetric and public key encryption, which is that symmetric encryption is very strongly provably secure in some sense, as long as the keys are secure, whereas the public key encryption relies on the difficulty of a math problem. And the trouble is that even though no one knows how to solve those math problems more efficiently, no one can prove that you can. So there's that problem. Okay. That's QKD. So I'm going to pause here because then we're going to go into entanglement. So I want to see if there's any questions about a qubit, preparing a qubit, and measuring in different bases or measurement disturbance or anything that I just talked about. And I'll get some water.
So QKD also needs a classical channel, right?
Very, very good point. And I will emphasize that a little bit more when I talk about entanglement, but you're right. As I was saying, I said Alice or Bob says this, tells the other something. You need a classical channel to do that. More importantly, you also need an authenticated classical channel because you need to trust that the classical information is correct. Because if it's fine if everyone knows that information. It doesn't bother the security, but it needs to be accurate. So you need to be able to trust that channel is authenticated, which, by the way, takes key information. You can do that with a cryptographic, with a pre-shared secret key. So properly speaking, quantum key distribution is a key expansion protocol, not just a key generation protocol. It takes some pre-shared key that you send, and then it just continuously refreshes it and expands it. So if you ignore the beginning, it is a key distribution protocol, but it requires that first part. So you have this shared key for the authentication of the classical channel. And just to put a finer point on that, basically all quantum communication, anything, requires a classical communication channel. It's always going to be part of the deal. And you'll sort of see why in a second, but even more so. So we've been talking about single qubits, in this case photons. Now I mentioned there's a lot more there in the sense that you've got this surface of these spheres representing the individual qubits, and you've got superpositions of states. Well, if you get multiple qubits, which is basically qubits are individually addressable, you can measure one without physically having to touch the other one. So that's why they're subsystems, is what a physicist would call them. If they're completely independent, they're just they're just completely independent mathematically, and you can just write everything out in sort of the algebra simple, so that all the superpositions sort of factor separately, and you can focus on each individually. But that's a special case. In fact, it's an extremely special case. Most of the states that you get, if you have multiple systems, if you allow interaction between them so that you can measure pairs of them together or prepare them in some, all the preparation ways, the bases essentially for the full space, there are many more of them than there are individually for the qubits. Because remember, you basically prepare a state by measuring it on a particular basis and getting an outcome. That's really how physicists prepare a state. If you have more than one qubit, as you add qubits, there are many, many more ways you can prepare than there are just sort of the sum of 2 times n. It's more like 2 to the n, right? So in this case, they're equal because n is 2, but it's interesting physically because this is a particular basis of states for 2 qubits. I could write a basis. This is in fact a basis for 2 qubits, but it's a basis chosen such that if I'm just making measurements on one or the other individually, I don't know anything about the individual states because this is a well-defined definite state. But if you look at it in terms of the individual, so this register, quote unquote, is if you think about it in this vertical basis, the horizontal vertical basis, this is 0. The second qubit is 1. This is 1. This is 0. So these are antisymmetric, so they're oppositely correlated. If I were to individually measure them in the HV basis, I would see that they're always oppositely correlated. If I'm comparing one of these 2 states, then they're always correlated. So correlation is great, but is that all there is to this? Is this just a weird way of writing classical correlations? And that's sort of what we're going to talk about next. First to say, this is called entanglement when you have a state prepared where you have the situation where measuring, you don't know, well, to be even more precise, if you were to ask me the question, what's the state of first qubit? Is it a 0 or 1? I don't know. And in fact, I don't know for either. So in terms of the Bloch sphere, it's actually the center of the Bloch sphere represents that. Not even a point on the Bloch sphere. It's literally, there's absolutely no information about it. It's not even in a quantum state in an individual sense. Like it is in a state, but it's in a state, and the only way to represent it is in terms of the other qubit as well. So it's in a state, the system is in a state, but the subsystem is not in a particular state. Sort of how to think about it. So the 2 qubits are in one of these states, but if you say what's the state of one qubit, first qubit, the answer is I don't know. Fundamentally don't know. Not that no one told me. There is no individual state. That's what I'm trying to get at. Now that sounds crazy and a little weird, and it is really weird and maybe not so crazy, but it does sound crazy. So that's why I have this spooky or awesome thing here. So that sounds spooky. There's a thing that it's in a state. How can a physical system not be in a state? What does that even mean, right? Well, it's not in a state in the sense that it's on that Bloch sphere. It's in a state, there is a mathematical representation of that state. It's math. You can always represent things. But in terms of thinking about it in terms of physical properties of that, say, polarization of that photon, if we want to use that physical system as an instantiation of the qubit, there is no answer to the question, what's the polarization of that photon? The question doesn't mean anything if it was prepared in that state. In the sense, now if I make a measurement on that qubit and I measure the polarization, I'll get an answer. And then it makes sense to ask that question. Because what's going to happen is once you measure that state, it will be in, say, a 0 state, say the horizontal polarization. Well, as soon as that happens, and say it was prepared in that state, if this was horizontal, you know the other one's also horizontal. So you now know the other one's horizontal. So it's also in a definite state now. But it's also not in the state you started with, right? So the first state was in a definite state, but only with respect to both qubits. You measure one, you prepared both qubits in a definite state, but they weren't in a definite state of polarization beforehand. So that's the distinction that's I'm trying to make. So that act of sort of creating the state by measuring one, this is the spooky part. It's in a definite state, and we can write it, but if you ask me what's the polarization, I'll say, I don't know, let me measure it. Okay, now it's horizontal. Okay, and you say, well, what's going on there? Wasn't it just always horizontal and you just figured it out by looking at it? And the answer is no. And I want to convince you of that, and that's going to be part of what we're going to say, work toward. That's the spooky part, which is that you sort of create that state, that local state, by doing the measurement on the entangled state. And also think about the fact that you have free choice of which basis to measure it in, and the fact that you will always get one of the two states that are outcomes for that particular choice of basis. So you have a lot of freedom of creating that local reality in some sense. The statistics are governed by these states and the correlations between them. But if you didn't want a horizontal vertical state, but you wanted one that was, say, diagonal, anti-diagonal, you measure in that basis, the plus minus basis, and get a 0, you know it's a diagonal in one direction, and it'll be in that direction. So you've disturbed it in a particular way based on your choice of measurement. The funny thing about these states in particular, though, is that these are 0s and 1s, sort of generally speaking, but if I put the physical things in here and said, well, this could be plus, minus, plus, etc., I could also write this in terms of horizontal, vertical. You can just put in the H's and V's and replace all the 0s and 1s with those because they all look the same. So the representation doesn't matter what the basis is as long as it's one of those fully conjugate bases, the three colored ones that we had. They all look the same mathematically. So all of the statistics look the same, but the outcomes of the states are different. So you can choose, in some sense, which of those pairs you want to instantiate by making those measurements. In some sense, you can measure the other state and prepare it remotely by making a measurement on the other. And that's the spooky action at a distance that Einstein didn't like. Now, this is a little bugaboo of mine about Einstein. A lot of physicists are very smart people. They all are generally smart people, but they also get a little uppity about Einstein. Einstein was pointing this out in the 20s, by the way. He was saying, look, this kind of thing can happen in quantum mechanics, and that sounds weird to me because how can influences travel faster than the speed of light? This isn't fast. This happens instantaneously, at least in terms of the way quantum mechanics is represented in terms of these states. So that doesn't sound right to him, and so he objected and pointed this out. And everything I'm going to say after this is actually going to point out how he was wrong, but I wanted to give him credit for making the point that that is an implication of quantum mechanics that almost no one cared about until, I would say, the 80s or the 90s, except for a few crazy people like me and a few others who still looked into the quantum mechanics, quantum information, and quantum foundations. And this guy up here, John Stuart Bell, who was the guy who took Einstein's questions and then took them even more seriously and then made a definite physical prediction. He figured out, well, this isn't just philosophy. There's a physics question here, and we can actually delineate, be precise what Einstein's intuition was and show that it's inconsistent with experiment, showing that quantum mechanics is consistent with experiment, but Einstein's viewpoint doesn't hold experimentally. So, spooky or awesome? Well, they're both. It's spooky, true, it is awesome. This gets into the question of how is this different from just classical correlation, which basically comes back to what I was saying earlier, is that classical physics doesn't have this idea of this sort of disturbance, where you have this instantaneous disturbance. And so that's freedom of choosing bases essentially makes this different from what I'll show in the next slide, which is a starting point for Bell. Bell was a great writer. You should look at some of his writings. This is from a paper called From Bertelsmann's Socks and the Nature of Reality. Bell was a theorist who did, his day job was a particle theorist. He worked working on the statistics of the outcomes of detectors at CERN. But he kept thinking about Einstein's questions, and it bothered him, so he wanted to get the bottom of it. So he went on sabbatical and then came up with all the things that I'm going to talk about Next, well, one of his colleagues was a mathematician by the name of Bertelsmann, and Bertelsmann, this is true, he's a real person, and his name, and he in fact does wear colorful socks, and they're never the same color. He's been doing it for decades. So he wrote this paper to say, well, how is this entanglement idea any different from just classical correlation? Because after all, this guy's socks are always mismatched. If you see one, you know the other isn't. You haven't seen it, but you already know. So by looking at that sock, it's not changing the color of his other sock from, from pink to not pink. It's already not pink. This is just correlation. This is what we, this is all the whole point of physics, is that things are correlated and you can predict them. So, but that is assuming that it had a definite color, right, before you looked at the first sock. And so he had a preamble for one of his talks about, this is not, because at the time he was arguing with a lot of people, and some philosophers were like, this is just correlation. What are you making a big deal out of? And he said, this is a little bit different. So this is how is it different? So we're going to get into something called the CHSH game. So there's a whole thing on Bell's inequality, Bell's experiments, and things like that. This is essentially equivalent to it, but it's a little bit easier to encapsulate. And this was invented in 1969 by Clauser, Horn, Shimoni, and Holt. Clauser being the guy on the left there who just won the Nobel Prize in Physics. Bell would have already won this, but he died young, unfortunately, before all this blew up and people took it seriously. They started taking it seriously right before his death, but the Nobel guys are very slow. They have a backlog on giving out Nobel Prizes, let's just put it that way. But they don't give it out posthumously, so he didn't get a share of the prize. These are all great scientists. Clauser did this as a grad student. Everybody told him he was crazy. He was doing experiments to try to show the kind of weird things we're going to talk about. He did it. He laid the groundwork for the next guy, who's Zeilinger, who did some extremely beautiful work in Austria over the last few decades. And then the other person there on the right is Alain Aspect, who's a French scientist who basically took what Clauser did in the 70s and perfected it in the 80s. So these are experimentalists who've shown that the thing I'm about to show you is a real thing. Okay, the CHSH game is sort of a game that we're going to try to win using quantum mechanics, but let's start out with just classical bits. So what's the game? Well, it's not really exciting, but that means it's simple, hopefully, right? So Alice and Bob, the game is that they're going to be given two random bits. Alice will be given some bit X, 0, 1. Bob will be given a bit Y, 0, 1. They're going to be given these bits in separated sealed rooms. And the objective of the game, to win, they have to satisfy this equation. So Alice's bit times Bob's bit needs to equal Alice's output plus Bob's output. Plus here being modular of 2, so these are bits. So 1 plus 1 is 0. So 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 0. And then, multiplication, right, 0 and 1. So that's it. If that's always satisfied, whenever it's satisfied, that's a win. And if you can look at the statistics if you do this a bunch of times. But the important point is they can talk ahead of time about how they want to do this, but they can't share any communication. There's no communication between them during the game. So I'm going to reveal how this works classically, but I want to see if anyone knows what the maximum probability of winning this game is classically. 50%. Always a good choice. Always a good choice. I'll give you a hint. There's 2 bits. That tends to mean you should cut it in half again. So there's actually a 75% chance. There's one strategy that wins 25% of the chance, and there's a bunch of strategies that win 25% of the chance, and there's one that wins 75% of the chance. And that's they just always say 0. The output is always 0. So that means they're always going to win unless X and Y are both 1, which happens 25% of the time. Then they're going to lose. And that's what this slide says. It's pretty straightforward. You can just write all the combinations down and look at it. There's some philosophy people who have some questions about stochastic things, blah, blah. It doesn't matter. All the randomness in the world won't make this any. The deterministic strategy is the best strategy. The best strategy is this strategy. It's simple. Again, not very exciting. Now, what I'm about to say is exciting. At least I think it's exciting. By the way, if I'm really long, let me know. We're almost to the point. If Alice and Bob have quantum resources, they can do better. If you really think about that for a while, so after you've had a few beers tonight, think about this and think, well, how does that work? How can you possibly win by more than 75% of the chance if you're not communicating? And also, by the way, entanglement doesn't allow you to communicate. You know, all the mystics in the world will make you think that you can commune with God or do instantaneous transmission of information, all those things. The God thing's between you and God, but the information transfer is not going to happen. There's no communication with entanglement. You can't send information using it at all, much less instantaneously. So how do you use entanglement to win this by more than 75% of the time? Well, this slide hopefully will illuminate that. So everything we've been building toward is to figure out how this slide works, right? There's the particular state they're going to share every time. It's that particular Bell state. It doesn't really matter. They all work, but it just changes the details. They're correlated, 0, 0, 1, 1. We can do this in any basis, choices of basis, but we're going to focus on that real part sector, which is that circle, which goes from here around the middle through the plus minus. So basically, they're going to each get 1 qubit from that pair each time they run the game, have a perfect quantum memory, so they don't have to worry about decoherence, which I'm sure Raphael talked about on Monday, but I'm a math guy. I don't care about that. Everything's pure and everything's happy. So they take their qubit, they get their X or their Y, depending whether it's Alice or Bob, and based on that, they measure in a particular basis. Just like we were saying before, you've got a free choice. How do you want to measure that qubit? They're independent, physically independent, but they're connected in the sense that the state is a well-defined state for both systems. So measurement disturbance prepares Bob's state if Alice measures in a particular basis. So if Alice measures in a particular basis, it prepares Bob's state. So if Alice sees a 0, she's going to prepare it in this sort of standard basis. Think about it horizontal, vertical again. And if it's up here, the horizontal state, she'll get a vertical. She'll say it's a 0. If it's the vertical state, she'll say it's a 1. If she gets a 1, she'll measure in the plus minus basis. And similarly, if it's a plus, she says it's 0. If it's a minus, she says it's a 1. Bob does the same thing, but he picks a kind of a weird basis. If he has a 0, he's going to measure in a basis which isn't actually on this figure. It's actually halfway along this circle connecting plus and 0. So I think in terms of the measurement rotation, his measuring device will measure something that's sort of halfway between. This is into the sphere. This is on the circle. There will be a state, say, here along this circle. That will be halfway between that, and that will be 0. There will be another one here. Here, which is sort of near this state, which will be the 1 state. So if it's 0, he measures in that state, so he'll get a state here or a state over there. And it's 0 if it's over here. It's back here, he reports it as a 1. If he sees a 1, though, he measures it in another basis. There's actually 2 choices here. I picked kind of the weirder of the 2, unfortunately. So that's one that sort of rotates to here and then a little bit further. So it's sort of like that rotation, but in the other direction. And again, you'll have 2 outcomes. And the one that's on this side of this pink line, he says it's a 0. If it's on the other side, he records it as a 1. That's it. That's the strategy. You do this a bunch of times and look at the statistics. And the answer is that you will win 1/2 plus the square root of 2 over 4. And I use that because the decimals are a little bit weird. It's like, well, why is it that fraction? Well, that's a very beautiful number that pops up a lot in lots of quantum information. I won't get into why, but that particular states that you get out from that weird measurement that Bob is making are actually called magic states in quantum computing for a different reason, but it's the same states for the outcomes of his measurement that maximize your win chances in this game. And if you think about this in terms of the Bell inequality, if you go look in that literature, all of those things about Bell tests and Bell inequality violations, the maximum violation is equivalent physically to winning this game with the maximum probability. So they're physically the same thing. So testing that is winning this game and vice versa. So this picture is a nice picture of these young guys in this lab in the Netherlands. People have been chasing a loophole-free demonstration of that sort of maximal win of that game or violation of Bell's inequality for decades. And in 2015, they finally had an experiment that closed all the loopholes. At least the consensus is there's always a few I won't say crackpots. I'll say there's always a few die-hard realists of a particular sort, if you know, you know, who say, well, there's always another loophole. Well, there are a few loopholes in that sense, but most people don't care, let's put it that way. So that gives you a sense of where we're at. We've just now get to the point where we can sort of easily maximally violate that game or violate the classical bound of that game. And that's a quantum communication problem to be able to do that, right? To be able to transfer those qubits from point to point, protect them, make the measurements on them, see those violations. It's sort of a basic physical resource that we're utilizing in quantum networking. Okay, I'm gonna have to go really fast now. Quantum teleportation is simple now. Quantum teleportation, the whole point of it is that it's actually a way of using classical communication and pre-shared entanglement like that we just saw in the CHSH game to actually send an unknown quantum state, any point on that Glock sphere that we don't know what it is, we just know it's there somewhere. We can't measure it because we won't want to send it somewhere else for them to use it. So we don't want to look at it. Someone just hands it to us and we want to send it to the next person. That transfer of that information, one way to do it is literally to physically hand it to someone. The other way to do it is to physically send the qubit through the channel, but a better way of doing it would be to have pre-shared a bunch of entanglement, stored it up, and then have classical communication and some protocol to use that to send it. So when the idea is that it's here, you make some measurements on it, and it ends up over there. So it's literally teleportation. But in the sense, it's not that, which is unfortunate. Maybe one day it will be, but right now it's not so much. Now, they invented that because it's really expensive to move people around on a TV show and have new sets, but it's easy to just pretend somebody goes from here to there instantaneously. So it was just a device to make their budget go further in the original series. It's a little more, it's more important in our case, right? Because this is now a primitive, a quantum communication primitive that lets us send pure, very high quality quantum states as far as we want, as long as we have a network of pre-shared entanglement. And that's what a quantum network, that's the point of a quantum network, is to be able to send quantum information throughout any of the nodes in the network. So this is going to be a little bit high level, but the idea here is that Alice has a qubit. She doesn't know what it is, but it's sitting in her memory. She also has one qubit that she got from an entanglement source. So this qubit comes in and she has that. She has her qubit. The other one goes to Bob. He holds it there. They store a bunch of the shared entanglement up in their local memories. Then if she wants to send this qubit, she brings it next to this qubit. She does this. As BSM stands for Bell state measurement. Remember, the Bell states are a basis for the two qubits. So if we've got two qubits next to each other, there's a measurement defined by those bases that projected into one of those four states. That's what a Bell state measurement is. You get two classical bits out that say, here's which one of those four states it prepared. So she does that, she gets those two bits out. She sends the two bits via a classical channel over to Bob, and based on what those bits are, he applies a local transformation to his qubit. It basically rotates it or not, depending on what those, in a way that's dependent on those two classical bits. Then the math works out to say, he still doesn't know he doesn't know the state, but he knows it's whatever that state was. And now, now that's in his memory instead of the qubit, the Bell state. Now there's no entanglement left because this broke the entanglement with his, but it did send this over there. So you consume the entanglement as a resource to send the quantum information across the network with the classical, closing the loop with the classical channel. So then you can sort of bootstrap that idea and generate entanglement between distant parts, right? That was just people next to each other. Well, if I have those quantum, if I have a bunch of people in the network, so there's Alice and there's Bob, but there's a Charlie in the middle, he's sharing entanglement with them, but they're not in sharing entanglement with each other. Well, there's a measure, you can do a Bell state measurement here, and then sort of teleport the entanglement from Charlie to Alice and Bob. So it destroys his entanglement with them, but it creates entanglement between them at the endpoints. Okay? And remember, we need classical communication to do all these protocols. If you do this in a network, this is a quantum network. This is what the quantum internet looks like. You've got a bunch of people in a network. Here's Alice and Bob again. These are other nodes in the network. These things are generating entanglement. They're being stored in a memory at each location. This represents a Bell state measurement. These are all sitting in a node, and there's all kinds of entanglement between all points. But if I want an entanglement between Alice and Bob, I can make measurements on these points to then do the teleport the entanglement across the network to connect them. And then they can send then they can send quantum information very far distances without any degradation. And that's the idea. This, by the way, has been done at a very small scale. It's very hard to do. The bit rates are very low. I'd say we're in the neighborhood of electric telegraph. This is like the 1840s of quantum information networks. They're networks, they're quantum, but they're not quite this yet, at least at a large scale. So that's what we're building the technology to do. So that's what it is, and here's a few of the things it can do that we know that it can do. Connect quantum computers, that's the big thing, because again, you can't just classically connect a bunch of quantum computers and get a big quantum computer. You just have, if you have 3 quantum computers and you connect them to classical communication, you have 3 small quantum computers. If you have 3 small quantum computers and connect them to a quantum network, you have something that's, cubically larger in terms of the quantum computational power. So that's a big enabler of large-scale quantum computing. There's a thing called blind quantum computing, which is like quantum computing in the cloud, but they don't know what information you sent, they don't know what information came out, and the computer also doesn't know what algorithm it ran. So invitationally, complete and total privacy for the computation you're running on a distant machine, which is very hard to do, but theoretically can be done. End-to-end encryption in the quantum sense, and also connecting quantum sensors. You're going to hear Friday a little bit about quantum sensors. If you have a bunch of distributed quantum sensors, you can make a much more powerful sensor by connecting them to quantum networks. And that's what we know we can do with them, but we're not even sure what we can do with any of these things. Quantum computing is going to have a lot of implications that we don't know yet. Quantum communication will be the same way. So that's that. So thank you for your patience and your attention. And
thank you. I think we have time for some questions, right?
Yeah, we can do a couple questions if people have them.
So one of the questions we've been asked is, so when is that going to happen? When do you have the equivalent of all the intranets coming together to form the internet? Is that a 10-year proposition or a 15-year, 20-year proposition? Just a rough estimate.
well, I'll say 2 things. I'll give you an answer, and then I'll tell you the answer is probably meaningless. The answer is probably 10 years. It's always a safe answer. I will say the reason it's hard to predict is because technology, all these things are being developed at the same time, and they're all synergistic. So developments in quantum computing and or quantum networking or sensors, all those things sort of feed into each other. So some breakthroughs can quickly happen successively and independently that just build capability very rapidly. I would say that I personally think that large-scale quantum computing will happen within 10 years. And I think quantum networking will also take about the same amount of time because I think they're going to be slightly different. There's overlapping but slightly different requirements. In some sense, networking is easier, but also there's some things about it that make it a little bit more difficult too. Also, there's a little bit less money focused on networking than computing, but That's starting to change as a lot of the computing people realize they need more networking capability. So I think there's going to be a lot more focus on the synergy of the two, and I think that will eventually pay dividends. So it's just a matter of how fast that happens. Yeah.
Any other questions?
This is maybe a dumb question, but as far as like power systems and the networks are concerned, electricity could be dangerous. So I'm thinking of a safety standpoint. Is quantum networks safe in a sense where you're tampering with entanglement, degeneration, all these kind of things, or is there going to be like, if you build a large scale one, do you have to be careful when you come in contact with it, come near it, things like that?
Well, the good news is this is much safer than even classical networks in some sense, because the energy part in particular is very low because we're manipulating single photons. So that's, the numbers are sort of large, multi-tens of billions of times smaller than the amount of light energy that's in a classical optical network. There's very low energy requirements in terms of that. So the entanglement is a physical resource. So I'm glad it came across that way. So it is a little bit like electricity in that sense, that you're distributing a physical resource. But from the point of view of power or any other sort of dangerous physical implication, yeah, there's no problems there. Unfortunately, it's such a fragile thing that we spend a lot of our energy protecting it and not worrying about protecting us from it. We don't have to worry about it harming us. It's more like us and our environment harms it. So we have to build technology to sort of insulate it from us instead of the other way around. That's the way I would think about it.
Thank you so much.
Thank you.